Welcome back, structural geology fans. The most common rock type at the Earth's surface is sedimentary. And since sediments accumulate at the surface, they start their existence as horizontal layers. But the occasional stresses in the Earth's crust can cause these layers to tilt from their original horizontal position. As layers are basically planar objects, we can take the strike and dip of any sedimentary layer, and in truth, the majority of strike and dip measurements are taken on sedimentary rock layers. But it would be far from correct to say that this is the only feature that strike and dip can be used on, nor would it be correct to approach any sedimentary surface and assume that a strike and dip measurement on that surface would represent the orientation of the sedimentary bed. Let's investigate that problem first, before moving on to what else can be measured with strike and dip. In our primary sedimentary structures episode, we discussed the formation of cross-bedding, planar surfaces that cut across the actual bedding of the sedimentary layer. If we see evidence of cross-bedding, we need to be very careful what a planar surface actually represents. The surfaces seen in this rock formation are mostly cross-bed surfaces, and if you took a measure on these thinking that it was a bedding surface, you'd be dead wrong. You can certainly take strike and dip on these cross-bed surfaces, but note that that is what you are doing. But even if a sedimentary rock has crossbeds, then we can almost always find an actual bedding surface. Recall that crossbeds curve so that they meet the upper bed with sharp angles closer to 90 degrees and blend in at a lower angle at their base. By recognizing these bounding surfaces, you are seeing the actual bedding plane of that layer of sediment. If such a bedding surface is exposed well enough, you can take a measurement. But layers of sedimentary rock, or even layers of volcanic lava flows or sills and dikes, are not the only planar features we can take strike and dip from. Faults are generally planar features as well, though we noted they can be fault zones. But it should be further noted that even within a broad fault zone, there are often smaller fault surfaces that can give the general orientation of the faulted zone. Joints are also planar features that can be measured, and we can't keep using the same symbol on maps for all these structural varieties. We saw in the last episode that the strike and dip of a rock layer is represented with this T-bar, with a longer line in the direction of strike and the short crossbar pointing in the direction of dip, with the degree of dip at its endpoint. And before moving on, we point out that we use relatively thin black lines to draw out the contacts between rock units, and we can even put a dip symbol and value on such contacts, if known. If instead we have measured a fault, or a joint, or cleavage plane, we're going to need to use separate symbols on our map to allow differentiation. The problem for the beginning geologist is that if you search geology map symbols online, you will find everyone uses the same basic strike and dip symbols, but there's enough variance in symbols used for features other than bedding planes to cause confusion. But we strive for consistency in our students from Colorado School of Mines, and this is the set of symbols we teach our students and that we use in the field. When measuring and recording faults, we can use a variety of symbols depending on the depth of information we can get about the fault. We use a solid dark line, and we do use varying sized pens to give lines with different meanings, different thicknesses, but we use a thicker line for faults and make them solid when we know there is a fault, but we may not know its orientation or relative movement. We use a dashed line when the same is true, but we are not certain of exactly where the fault is. You can always make a dashed line solid if you get more confident about the fault location later. A difference in rocks on either side of a valley may indicate a fault, but it may be buried under eroded sediment down in that valley somewhere, so we can only guess where it is and use the dashed line. Larger spaced dash lines are saying we are really not sure where the fault is, but we think it's there. And putting question marks between the dash line says there may be a fault, but its very existence is uncertain to us at that point. With a bit more information, we might be able to say where the fault is and the exact strike and dip of its plane. If we don't know which side went up relative to the other, we can just use an arrow on the side of the strike line in the direction of the fault dipping into the ground with the angle of dip at the end of the arrow, or a crossbar if the fault is vertical. Faults often have slicken sides, which are a lineation that may be at an angle to the dip direction, and such lineations can be represented with a short arrow perpendicular to the line for the dip direction, and a longer arrow for the lineation, which we'll talk about measuring lineations in a moment. So we use separate dip numbers, as lineations not parallel to dip will always have a smaller dip angle than the true dip of the plane. If we do know the relative movement on each side of the fault, we can denote vertical motion by placing a solid block or stick and ball on the down-thrown side of the fault, or a U on the up-thrown and D on the down-thrown sides of a normal fault. This stick and ball symbology, though, is cleanest in that it can be placed in a manner that does not blot out important information on the map, and the solid block can be confused with the symbol for joints, so stick and ball is preferred. With horizontal motion on a strike-slip fault, we just use opposing arrows showing the relative movement on the fault. Lastly, thrust faults are usually shown with triangular teeth on the hanging wall side of the fault or a T on that side. If we measure a joint, it is an open blocked area on the side of dip, though you see here it can be represented by a solid block as well, in which case don't use that same symbol solid block for a fault symbol. So with these varied symbols, we can tell other geologists if we were measuring bedding of a layer, a fault plane, what kind of fault plane and how certain we are, or joint surfaces. But wait, there's more. Not only can you measure physically flat surfaces with strike and dip, you can measure other conceptual surfaces as well. Imagine a foliated metamorphic rock, one in which rod or plate-shaped minerals have all lined up. The rock may have begun as a sedimentary rock or a lava flow that has a bedding to it that can be measured, but it also has metamorphic cleavage, which can split the rock parallel to its lined-up minerals easily and produce another plane, a cleavage plane. To denote we are measuring cleavage on a map, we use a triangle on the dip side of the strike line. Bedding, faulting, jointing, cleavage. With a folded structure, we can certainly measure the beds around the fold, and we noted previously that up-arched anticlines have beds that dip away on either side of the fold axis, the center of the fold, and that downwarped synclines have beds dipping in towards the center. But that leads us to another plane that we could measure, which is the central axis of symmetry down the middle of the fold. Taking our field notebook or map board, we can place it where we see the fold axis, that plane of symmetry, and take a strike and dip from that surface. We can quickly represent the axis of a fold on a map and show it to be an anticline using oppositely directed arrows off the axis, a syncline using converging arrows on the axis, or a monocline with one arrow in the direction of the lower limb of the monocline. We can even use these special symbols to show the axial direction of minor folds within a larger fold, the vergence of the minor folding. But recall that some folds, most actually, are plunging folds, diving one end into the earth while the other end sticks out at the surface where it tends to get eroded into the V shapes we saw before. The plane of symmetry tells us the direction in which the fold plunges, but not the angle. That will require another type of measurement than the standard strike and dip we've been discussing. The direction and angle of fold plunge is a line, not a plane. And with such lineations, we switch to measuring dip and dip direction. If we point our compass exactly in the direction a fold is plunging, then we can read off the dip direction of that fold. We then use the dip indicator on the compass to measure the angle of this dip from vertical and place this arrowed symbol on the map. The line of a plunging fold is not the only feature we can measure with dip and dip direction. Faults form slicken sides, and if present, we should not just measure the strike and dip of the fault, but the dip and dip direction of the linearly scraped slicken sides as well. And place this arrowed symbol on the map. Glacial striations, grooves in rock from massive ice sliding over, are linear features we can measure with dip and dip direction, or the trackway of an ancient organism, or flow patterns on a surface. Crenulations that form in metamorphic rocks present themselves as linear features on the surface of foliation planes and can be measured with dip and dip direction. Just remember that when measuring a planar surface, we can use strike and dip, but when measuring linear features, you use dip and dip direction. But here's a curveball for you. What if a planar feature gets exposed at a planar surface? It sure looks like a line, but it's formed by a plane. If the plane intersects the surface at a 90-degree angle to its strike, then the angle we see of that line, the dip that we see there at the surface, that's the true dip of the bed. But if the plane intersects the surface at anything other than 90 degrees, it will show an apparent dip, less than true dip. If you think about it, a plane hitting a surface head-on will look like a horizontal line, even though the planar feature making it is dipping. But not all hope is lost, as we can use a little trigonometry to calculate the true dip as the plane of observation cuts the plane of interest from its apparent dip. Either of these formula will work, the first using the strike of the plane in question, the second using the direction of true dip. The apparent dip can never be greater than the actual dip, and that is the case when we take a cross-section exactly perpendicular to the strike of the plane. Take a cross-section parallel to the strike, and the apparent dip will be 0, a horizontal line. Take a cross-section at any other angle between 0 and 90, and you will get a line with an apparent dip at a smaller angle than the true dip, getting smaller as your cross-section becomes parallel with strike. And if you have an intersection of cleavage planes with the bedding planes, or bedding planes with lineations, we can use these combinatorial symbols. I have placed a copy of this symbol chart on the iTunes note page for this course, so feel free to download for your own reference from there. In the field, we can usually tease out the actual dip of a striking planar feature, but as we collect our data and fill in our map, we get to a point where we want to extrapolate what we've seen on the surface to what we think exists down below us. To do this, we make cross-sections below the line of a topographic profile, which does not always cross our known planar features perpendicular to their strikes, and so we will have to use apparent dip angles to represent what it would look like below our cross-section line. Now, the first step in making a geologic cross-section is making a topographic profile, which was episode 11 of this series, so if you feel rusty on making topographic profiles, watch that episode again before going on. But you can't get at the cross-section under the topographic profile until you've made your geologic map. Since you are basically at the point where you can get out there and get to work, we will spend some time in the next episode to discuss field mapping equipment and safety, here on Earth Explorations.